All right, today's lesson focuses on left-hand and right-hand limits. We began to talk about them in a few previous videos. An overall limit looks at what the graph is doing on both sides of an x value. A left-hand or right-hand limit examines on just one of those sides. So for example, a left-hand limit looks as the x values are approaching some number from the left and sees what is happening with the function. It is denoted by a negative sign after the value. So an example of left-hand limit with actual numbers or an actual function in there, say we had the limit as x approaches 2 from the left is how that would be read, of maybe x squared plus 2. And we would say as our x values get really, really close to 2 from the left-hand side, so like 1.9, 1.99, 1.999, our function's going to get closer and closer to 6. For a right-hand limit, we would look at values that are coming from the right side. So if we did a similar example, if we looked at the limit as x approaches 2 from the right, and again, the right is denoted with a plus just after the number, and we'll just do the same example, x squared plus 2. So we would be looking at numbers like 2.1, 2.01, 2.001. So no, x values that are getting closer and closer to 2, but just from the right side. In this case, it would also be 6. We talked about the other day that in order for the overall limit to exist, that left-hand limit and the right-hand limit must be the same. Therefore, that's why it's important to be able to evaluate a left-hand limit and a right-hand limit on their own to determine if the overall limit exists. So on the bottom here, this would be read as the limit as x approaches 3 from the left of f of x. So we would only look at values that are less than 3. Specifically, we would look at values getting really close to 3 from the left, so like 2.9, 2.99, 2.999. The bottom one there, x approaches 3 from the right of f of x, we would look at values like 3.1, 3.01, 3.001. And then the middle one is our overall limit. That looks at values from both sides. And for that to actually take on a value to exist, it would need to be approaching the same thing from both the left and the right. So often when you're evaluating the middle one, the overall limit, you have to look at the left-hand and right-hand limits individually. Now an important theorem is the one I just mentioned on the previous slide. In order for an overall limit to exist, okay, so here we have the whole limit coming from both sides. It must be true that the left-hand and right-hand limits are actually approaching the same number. We saw in the previous video the Heaviside function. When we had the limit from the left, it was approaching 0. The limit from the right was approaching 1, so therefore that did not exist because the left-hand limit did not equal the right-hand limit. So for the overall limit to exist, the left-hand and right-hand limits at a given value must be the same. So, based off this graph, let's look at these 3 questions. So start out, is x equals a in the domain of f? Well, it'll be in the domain if at that x value, the function takes on some y value. And you can see at a, we do take on a y value. So yes, it is in the domain. Next, we want to know if the limit as x approaches a exists. Well, if you look ahead to part C, we want to know, is the right-hand limit and the left-hand limit equal? So it might be useful to answer part C first, because we know for part B to exist, the left hand and right hand must be equal. So let's go ahead and look at part C first. As our x values approach a from the left, and as our x values approach a from the right, notice our y values are converging on the same spot. Therefore, the left hand and the right hand limits are equal. And if your left hand and right hand limits are equal, then your overall limit exists. So it makes more sense to evaluate the left and right first, because that will basically answer part B for us. So looking at this graph, we want to find our limits at x equals 2 and x equals 5. Now notice we're talking overall limits here. At x equals 2, we will want to look at our left hand and right hand limits. So we'll look at our limit as x approaches 2 from the left of g of x, and we'll look at our limit as x approaches 2 from the right of g of x. So your actual limit value should be a y value, keep in mind. So as our function gets closer and closer to an x value of 2, our y values from the left are getting closer and closer to 3. As our x values get closer and closer to 2 from the right, our y values are getting closer and closer to 1. Our left-hand limit does not equal our right-hand limit. Therefore, our limit as x approaches 2 of g of x, we would say does not exist, DNE. And that is because the left-hand limit does not equal the right-hand limit. Looking at x equals 5 now, we'll look at our limit as x approaches 5 from the left of g of x. We'll look at the limit as x approaches 5 from the right of g of x. And then once we know each of those things, we should be able to determine our overall limit as x approaches 5 of g of x. So as our x values get close to 5 from the left, our y values are getting closer and closer to 2. Remember, the limit is not what's happening at the value, it's what's happening when you get close to the value. Sometimes those are the same, sometimes they're not. As our x values get close to 5 from the right, our y values are also approaching 2. Because our left and our right hand limits are the same, we therefore have the overall limit existing, and it will take on the same value as the left and right hand limits did. So our overall limit as x approaches 5 of g of x would just equal 2. What we'll do now is we'll look at a piecewise function. A piecewise function is a function that is defined differently depending on where your x values are. So we're going to say when x is less than or equal to 0, we're going to look at x squared minus 1. And when x is greater than 0, we're going to look at 2x plus 3. So first, for our x squared minus 1, we'll take x values like 0, negative 1, negative 2, negative 3, and so forth. So 0 squared minus 1 is negative 1. Negative 1 squared minus 1 would be 0. Negative 2 squared is 4, minus 1 would be 3. Negative 3 squared is 9, minus 1 is 8. And then it would keep going. Now it's helpful to somehow remind yourself your endpoint values where it changes. So in our case at 0, which should be closed and which should be open circles. So I like to just put a little closed circle next to that to remind me when I'm plotting it that it's going to be a closed circle at 0, negative 1. So I have a closed circle at 0, negative 1, then we go negative 1, 0, negative 2, 3, and negative 3, 8. And then the function continues to the left for that one. For our other half, we'll have 0, 1, 2, 3, and so forth in the positives. Now, you may be asking, why are we choosing 0 when it doesn't equal to 0? We need to know where to put the open circle. So I like to put a little open circle there, or sometimes even just write the word open next to it to remind me when I'm plotting that point, it should be an open circle. So when we put 0 into our 2x plus 3, we get back 3. 2 times 1 plus 3 is 5. 2 times 2 plus 3 is 7. And then when we put 3 in, we'll get 9. So at 0, 3, we need to put an open circle, because it's not actually taking on that value there. It's just after 0. We'll have 1, 5, 2, 7, and 3, 9. And then it continues. So this is an example of a piecewise function. You should have graphed some of these in pre-calc. And now we'll evaluate our limits. Our limit of f of x from the left as x approaches 0. Well, as our x's get close to 0, our y values are getting closer and closer to -1. As x approaches 0 from the right, our y values are getting closer and closer to 3. Because our left-hand limit does not equal our right-hand limit, our overall limit as x approaches 0 of this function does not exist, dne. Now, sometimes you can just think about the limits to figure out if it'll exist or not. Sometimes you can look at it graphically. So we're going to do both in this case. Let's first think about our left-hand and right-hand limits to see if our overall limit will exist. So when we're coming to 0 from the left, we're going to be having negative numbers. Those negative numbers will be really, really small. And then we'll square those negative numbers so they'll become really, really small positive numbers. So we basically got 1 over really small positive numbers. So if you have 1 over, say, like 1/100th, or 1 over 1/1000th, 1 over 1/10,000th, 1 over 100,000th, that's what we're going to be going towards. Well, by keep, change, flip, this is really 1 times like 100,000 over 1. So as we keep adding zeros here, we keep multiplying by another 0. So really, as our values get closer and closer to 0 from the left, our actual function value is going to get huge. And it's going to be huge in the positive way, so we'll go to positive infinity. Now, infinity is actually not a number. So technically, that limit doesn't exist because it's not going to a number. But we say that it goes to infinity because it is growing without bound. If we do it from the right now, it'll be a similar idea. We'll have really small positive numbers squared when we put them in for x. So like 1/10th, 1/100th, 1,000th, and those are all on the bottom. When you multiply by the reciprocal, we end up getting really huge numbers, so again, that's infinity. So our overall limit then must be infinity. Now you could have looked at this graphically as well. If we graphed 1 over x squared, it's pretty clear that as your x values go to 0 from the left, our y values are getting huge, going to infinity. And when you look at your x values going towards 0 from the right, your y values are also getting huge, meaning your overall limit is infinity. In this particular graph, we're saying our x value we're approaching is a. Well, a from the left is going down without bound. A from the right, our y values are also going down without bound. When I say without bound, meaning it's getting smaller and smaller and smaller. So we therefore are going towards negative infinity for this overall limit, because our left-hand and right-hand limits both equal negative infinity. In this particular example, as x approaches 0, our limit as x approaches 0 from the left of f of x, As our x values get close to 0 from the left, our y values get large positive numbers. So we'll go towards positive infinity. Whereas x approaches 0 from the right, f of x becomes large negative numbers. So that goes towards negative infinity. Our left-hand limit and right-hand limit are not equal, so therefore our overall limit does not exist. And you can see that in the picture as well. On the left side of 0, we're going up. Right side of 0, we're going down. So therefore, the limit doesn't exist. So some different pictures. We can look at our left-hand and right-hand limits individually as well. And sometimes they'll go to infinity. Like in this picture on the left, as we approach a from the left-hand side, it's clear that the y values are getting very large, so this would go to infinity. Same thing with the right-hand picture. As we approach x, or x approaches a from the right, the y values are getting large, so that goes towards positive infinity as well. Each of these pictures show graphs that go towards negative infinity at a. From the left and from the right, our y values are going towards large negative numbers, so therefore they're going to negative infinity. And if you piece them together, we've got our positive infinity from the left, positive infinity from the right. So we can then say our limit as x approaches a, our overall limit of our function f of x, must be positive infinity. And likewise, the other set of pictures, these were each our negative infinities from the left and from the right. So we can then say our overall limit of f of x as x approaches a must then be equal to negative infinity, because our left-hand limit and our right-hand limit were both that. The last thing we'll look at in this video is how to find vertical asymptotes and where they are located. Because at your vertical asymptotes, that is where you might have limits that go to negative infinity or positive infinity. So it's helpful to know where they are going to occur. In our first example, 2x over x minus 3, you should have seen in pre-calc when you graphed rational functions that the vertical asymptotes are just whatever makes the denominator 0. So you can set the denominator equal to 0, and we'll get that we have a vertical asymptote at x equals 3 for this first one. In the second one, we have a natural log of x. Well, logs have a domain of x greater than 0. The graph of every basic log passes through the point 1, 0. And then as you go towards 0 from the left, you get really large negative y values. So we would say that we have a horizontal asymptote at x equals 0 in this case. How that could apply to limits is I could ask you, what is the limit as x approaches 0 from the right of natural log of x? And when you're coming to 0 from the right, our y values are getting really, really small. So small going forever towards the negatives, so we go towards negative infinity. Now the overall limit at 0 would not exist because there's nothing happening on the left side of it. Only on the right side do we have a limit. Now our last one, tan x, we need to remember that tan x is really sine x over cos x. Well, based off our first example, the 2x over x minus 3, we talked about a rational function has a vertical asymptote when the denominator is 0. Well, this is now just a rational function. So we want to know, when is cos x equal to 0? Keep in mind that this year we will work almost exclusively in radians. So we have pi over 2, we have pi, 3 pi over 2, and 2 pi. Cosine always starts at 1 and will look something like this. Well, cosine is 0 at pi over 2. It's also 0 at 3 pi over 2. If we were to keep going, it would hit 0 again at 5 pi over 2. If we went the other way, it would hit 0 again at, oops, have one too many marks. It would hit 0 again at negative pi over 2. So notice all our places where it's hitting 0, our numerator, our number in the numerator with the pi is always an odd integer. So in general, we can say we have vertical asymptotes at x equals n pi over 2. And we would just need to say where n is an integer. So if we have 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, going the other way, negative pi over 2, negative 3 pi over 2, negative 5 pi over 2. Any of those cases is where we would have asymptotes. And the graph of tangent we would have our asymptotes at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. The graph of tangent would look something like this. So we can see those asymptotes would keep occurring every pi. Okay, every jump in pi at the odd pi over 2 integers. That's all for today's video. We'll see you next class period.